Welcome to Chapter 11 of Class 9 Science, Sound. In this fascinating chapter, we'll explore how sound is produced, how it travels through different media, its characteristics, how we hear it, and its many applications in our daily lives. We'll discover that sound is not just what we hear, but a physical phenomenon with amazing properties and uses. Get ready to understand the science behind the sounds that surround us every day. Let's begin with understanding how sound is produced. Sound is created by vibrating objects. When any object vibrates, it sets the particles of the surrounding medium into vibration, creating sound waves that travel through the medium. We can demonstrate this with simple experiments using tuning forks. When you strike a tuning fork and bring it close to your ear, you hear a sound. When you touch the vibrating tuning fork, you can feel the vibration. And when you touch a vibrating tuning fork to water, you can see the splashing caused by the vibration. This clearly shows that sound is produced by vibrating objects. Different musical instruments produce sound through different vibrating parts: strings in guitars, air columns in flutes, and surfaces in drums. Now let's explore how sound travels. Sound requires a material medium, solid, liquid, or gas, to propagate. It cannot travel through vacuum, which we can prove with the bell jar experiment. When we remove air from a bell jar containing a ringing bell, the sound becomes fainter and eventually inaudible. Sound travels as mechanical waves called longitudinal waves, which consist of alternating compressions and rarefactions. Compressions are regions where particles are crowded together, creating high pressure, while rarefactions are regions where particles are spread apart, creating low pressure. These compressions and rarefactions travel through the medium, transferring energy from the source to our ears. Sound waves have three main characteristics: frequency, amplitude, and wavelength. Frequency is the number of oscillations per second, measured in hertz. Amplitude is the maximum displacement of particles from their mean position. Wavelength is the distance between two consecutive compressions or rarefactions. These three quantities are related by the wave equation: speed equals wavelength times frequency. The speed of sound depends on the medium. It's fastest in solids, slower in liquids, and slowest in gases. This is because sound travels by particle-to-particle interaction, and particles are closest together in solids. Now let's discuss how we perceive different sounds. Pitch is how high or low a sound appears to us, and it depends on frequency. High frequency means high pitch, like a whistle, while low frequency means low pitch, like a drum. Loudness depends on amplitude. Greater amplitude means louder sound. Quality or timbre helps us distinguish between different sources producing the same note, like telling a violin from a flute. The human ear can hear sounds in the frequency range of about 20 Hz to 20,000 Hz. Sounds below 20 Hz are called infrasound, and sounds above 20,000 Hz are called ultrasound. The speed of sound varies in different media. In air at room temperature, sound travels at about 346 meters per second. In water, it's about 1500 meters per second, and in steel, it can be over 5000 meters per second. This explains why we see lightning before hearing thunder. Light travels almost instantly, but sound takes time. If you count the seconds between lightning and thunder and divide by 3, you get the distance in kilometers. The speed of sound increases with temperature and humidity, which is why sound travels faster on hot, humid days than on cold, dry days. Humans can hear sounds between 20 Hz and 20,000 Hz, but this range decreases with age. Many animals have different hearing ranges. Dogs can hear up to 45,000 Hz, which is why they respond to dog whistles that we can't hear. Bats and dolphins use ultrasound for echolocation. They send out high-frequency sounds and listen for the echoes to navigate and find prey. Ultrasound has many medical applications, like imaging during pregnancy, and industrial applications, like detecting flaws in metals and cleaning delicate parts. Sound obeys the laws of reflection, just like light. The angle of incidence equals the angle of reflection. When sound reflects off a surface and reaches our ears after the original sound, we hear an echo. For a distinct echo, the reflecting surface must be at least 17.3 meters away. We use this principle in sonar to measure ocean depths and detect submarines. Other applications of sound reflection include stethoscopes for medical diagnosis, megaphones for directing sound, and soundboards in concert halls to improve acoustics. As we conclude this chapter, let's review the key concepts. Sound is produced by vibrating objects and requires a medium to travel. It propagates as longitudinal waves with compressions and rarefactions. The characteristics of sound, frequency, amplitude, and waveform, determine how we perceive pitch, loudness, and quality. Humans hear between 20 Hz and 20,000 Hz, with ultrasound having many practical applications. Sound reflects obeying the same laws as light, enabling technologies like sonar. Understanding sound helps us appreciate music, communicate effectively, and develop technologies that improve our lives. Undefined.